Alrighty, howdy folks. Chapter 16, Section 3. The fundamental theorem for line integrals. Man, that kind of scares me. I remember somebody said, fundamental theorem of calculus. I was like, wow, that must be a big deal. Yes, it is a big deal. It is actually, when they say fundamental theorem, they do mean it. So let's get on with recall the part 2 of fundamental theorem of calculus. In fact, there are two parts to the fundamental theorem of calculus. One says, part 1 actually talks about the derivative of an integral. And here we have the integral of a derivative. Quite possibly this is not the form in which you saw this. Okay. Well, do you ever see something as the derivative, integral of a derivative dx, and that is f of that minus f of this? Well, you can take your, how should I put it? Okay, this is true, right? Suppose I say this is integral a to b of lowercase f of x dx. Then we say that is uppercase f of b minus uppercase f of a, lowercase f of x dx. And then what in the world is uppercase f? Well, uppercase f is the antiderivative of the lowercase f. For example, if I have integral of cosine x dx, then I don't evaluate cosine of b minus cosine of a. Instead, I go to the antiderivative of cosine x, which is sine of x, right? Evaluate sine of b minus sine of a to get the integral. Well, that is because the derivative of sine happens to be cosine. So the integral of cosine is sine. So if we have f prime of x, the integral of this would be just simply f of x. And with that, we are evaluating from b to a to b. Okay, all right, let me not spend too much time on this. So recall, now, how does it work with these line integrals? This is a theorem. Let C be a smooth curve given by the vector function r of t, with t going from a to b. And let f be a differentiable function of 2 or 3 variables whose gradient vector del f is continuous on C. What do we have here? We have a curve given by in its parametric form as a vector form. And also we have a differentiable function of 2 or 3 variables whose gradient happens to be del f. Now, let me tell you that this gradient is now playing the role of f prime of x. It's the derivative of f. It's a little bit more involved than a simple derivative like in Calc 1. But the concept is the same. The del operator is basically partial with respect to x of f times I plus partial f with respect to y j, like that, right? So del operator is like the derivative. And so what we can say is del f dotted with dr. Do we have to have a dot product here? Can we say del f dr? No, that would be wrong. Why? Because we have del f to be a vector and dr is also a vector. So we have a vector, comma, vector times vector. What do we mean by vector times vector? What kind of a times is it? Right? Is it the dot product or is it the cross product? When you're talking about the product of two vectors, you have to be specific whether it's a dot product or the cross product. You cannot simply say vector A times vector B. That has no meaning. Unless, of course, you get to tensors where that makes perfect sense. But right now, in our level, you have to say dot product or cross product. And here we saw earlier that we are talking about del f dotted with dr. Probably in the previous case we had vector uppercase F, the vector field F dotted with dr. That's what we integrated. And lo and behold, that turns out to be simply F evaluated at the upper point, R of B, minus F of R of A. So the idea is T is going from A to B. So that is sort of like the upper limit, B, and find out what the position vector at T equals B is, which is what R of B is. Evaluate the function F at that upper limit minus F evaluated at the lower limit. Cool. But notice, this has to be the derivative, the gradient vector del f. Who in the world is going to give you a gradient vector? Right? Usually, problems won't be where you are given a nice del f and you have to integrate that. But there is something that we are going to do about that. Okay. Then the next concept that we need to talk about is the independence of path. Okay, if C1 and C2 are two curves with the same initial and terminal points, does that make sense? If I have 2 points A and B, I can draw one curve C1 and I can between those 2 points, and I can also draw another curve C2, same initial and terminal points, right? So when we say integrate along a curve, are we merely interested in the points, endpoints, that is R of A and R of B? Or are we interested in the path that we take with that particular curve? Right? Does it matter? And the answer is, well, if you were to take two different paths, even though the initial and terminal points are the same, in general, the key phrase is in general, the two integrals are not the same. Okay? What do I mean by in general? There are for quite a few functions. You cannot automatically say, yeah, those two doesn't matter, man. The path doesn't matter. It's just that the integrals are the same. You cannot say that. But then, however, okay, by the way, would you agree that the initial and terminal points are this and this? So I can go along curve C1 or I can go along curve C2. In general, these two integrals would be different. However, in the event the two integrals are equal, then we call this F as a conservative vector field. Cool? That is an interesting one. The F is called a conservative vector field. And you will bump into conservative vector fields in both physics and in engineering courses. For instance, I wonder if work is conservative. Like, it doesn't matter which path you take, right? If you're climbing up a hill, does it matter which path you're taking to express how much work you've done? Nope. I think it's MGH is the work done. And excuse me. MGH is the work done, and your mass is the same, the gravity is the same, the height you have achieved, whether it is through a winding path or whether it's through a vertical path, height is going to be the same. So that is a conservative field. Okay, anyway, so in the event the two integrals are equal, we call it a conservative vector field. Now, closed path, what do we mean by closed path? A curve is closed if its initial and terminal points are the same. Well, I can illustrate that using this one. What if I were to have, okay, let me put it this way. Would we call this as a closed curve? Which one? If I start, say, at this point, traverse along this C2, come to that point, and then traverse back along the negative C1 and end up back at the starting point. Would that be a closed curve? Yep, that is a closed curve. Okay. Now, theorem. The integral f dot dr over a c, the line integral, is independent of path in domain D if and only if f dotted with the integral f dot dr is equal to 0 for every closed path C in D. What? Okay, let me explain that. Maybe I have mentioned this before. Are you familiar with this phrase, if and only if? The if and only if is, in mathematics, when you see that, that means the left-hand side, the stuff to the left of that if and only if, implies the stuff to the right of it. And also, the right stuff implies the left-hand stuff, the left side stuff. Usually, P implies Q does not mean Q automatically implies P. A Labrador, every Labrador is a dog, but every dog is not a Labrador, right? So, P implies Q does not necessarily mean Q implies P. However, there are cases where P implies Q is automatically, it is also true that Q implies P. For example, x equals 2 implies x plus 3 equals 5. X plus 3 equals 5 implies x equals 2. So in a situation like that, we say x plus 3 is equal to 5 if and only if x equals 2. Or x equals 2 if and only if x plus 3 equals 5. So, in light of that, what we need to read this as is, if integral is independent of path in the domain, then the integral is equal to 0 for every closed path C in D. Also, if the integral is 0 for every closed path in path C in D, then the integral is independent of the path in the domain. Okay? What else? What exactly is this trying to say? Now let's focus in a little bit more. If you find out that integral this from one point to another point is independent of the path. Okay. Are you with me? Let's say we have a vector field F and we integrate it along some particular curve from an initial point to a terminal point. And we find that no matter what path you take, that integral is the same. Then guess what? This integral on a closed path, meaning you go from here and then come back here, that integral is guaranteed to be 0. Right? And likewise, if on a closed path you find, if every closed path that you find that the integral is 0, oh, that means if I were to take any 2 points, 2 different points, distinct points, then doesn't matter what path I take to go from one point on that closed thing to another point. That integral would be independent of the path as long as the initial and terminal points are the same. That's what this is saying. Now you might ask, why? Why is that? That is because Does this explain that? Okay, no, maybe I'll explain it. If this integral, let's say if I take this path, I get a value of, the integral is 3. Are you with me? If I, golly, I'm sorry about that. So if I integrate along this path, let's say I get a value of 3. Now, if it is independent of path, then if I take this other integral, should I get the same value 3? Yes. Cool. Now pay attention to my question. If by going from this point to this point, I get a value of 3, what should I get if I integrate from this point to this point? If I reverse the points, what should that integral be? Right? Earlier we talked about a curve is called negative c if you flip the starting and terminal points, right? So in that case, it would be negative 3 would be the integral. Cool. Well, if you have a closed path, what would happen? From here to here, you get a positive 3, and from here to here, integral gives you negative 3. When you add them, you got to get 0. See that? Okay, let me put your minds at ease. If you understood all of this theory part of it, that's great. If not, don't worry too much about it. But it's a good idea to understand though. All right, with that, let's look at another theorem. Suppose F is a vector field that is continuous on an open connected region D. There's a region and it's all connected. There are no disconnection. What should I say? Discontinuity sort of things. Connected region itself, I can spend a lot of time. People in advanced calculus will talk about connected regions for a whole week. But in our case, if we just understand what a connected region is, that's okay. Okay, if the integral f dot dr is independent of path D, then F is a conservative vector field on D. What is that? If F is a vector field that is continuous on an open connected region D, and if the contour integral f dot dr, line integral or contour integral, line integral is independent of path in D, then F is a conservative vector field on D. In turn, what does that mean? This is the money statement. That is, there exists a function lowercase f such that del f is equal to uppercase F. Okay, let's focus on this one. If F is a conservative vector field, then you are guaranteed of the existence of a lowercase f such that del f is equal to F. Okay, what's the big deal about that? Look at this. Your objective, let us say, is to integrate F, uppercase F. But if you know that F is a conservative vector field, then you can find a del F, del lowercase f. Are you paying attention? Let me repeat that one more time. This is the concept that you must get. If your objective is to evaluate f dot dr, uppercase f dot dr, and one particular statement that is true about F is that it is a conservative vector field, then guess what? You are guaranteed that there is a lowercase f such that del f is equal to F. How does that help with integration? Let me go back. Would you see this? Your objective is to evaluate integral uppercase f dot dr, but uppercase f is nothing but del f, lowercase f, And what is the integral? All you need to do is f of r of b minus f of r of a. Okay, I'll solve quite a few problems. This is the integral we want to evaluate. That integral is nothing but equal to this integral provided f is a conservative vector field. And in that case, evaluating the integral is a pretty simple thing. You just evaluate this function f at the terminal point minus evaluate the function at the initial point. You're done. Okay, that's the beauty of this theorem. And I'll show you quite a few problems on this one. But before I do that, how do we figure out if vector f is a vector field f is conservative, right? So that's the question. Now, if some of you have taken differential equations, you will see something here that might be familiar to you when we talked about first order exact equations. Okay, if this equation is exact, how do you solve the differential equation? Okay, let f equal some pi plus qj, some p of xy or p of xyz plus q of xyz j. Because we okay, let's stay with only 2D, R2. In R2, we have f of xy vector field is p of xyi plus q of xyj. Then del f is equal to f. What does that mean? Del f is nothing but partial f with respect to xi plus partial f with respect to yj is going to be equal to this pi plus qj if this is a conservative vector field. Okay, that means partial f with respect to x must be equal to p, partial f with respect to y must be q, right? Equating the like components. The x component of this, if we are claiming, is equal to this, that means this must equal this, that must equal this, right? Now, recall that if the partial derivatives are continuous and differentiable, then we can say something. Second partial of f with respect to x and y is the same as second partial of f with respect to y and x. Okay, that means the order in which you differentiate doesn't matter. This one says, how do you read second partial f with respect to x and y? This is partial with respect to x of partial f with respect to y. Which means on the left hand, in the case of the left hand side, you will integrate f with respect to y first. And that resulting quantity you differentiate with respect to x. However, here we differentiate with respect to x first, and then we differentiate with respect to y. And what we learned is, regardless, the only thing that are the conditions is the partial f with respect to x and partial f with respect to y must be continuous. If that happens, then you are guaranteed that these two quantities would be the same. Okay, what's the big deal about that? The big deal about that is, now if I take a partial derivative of this quantity with respect to y, then on both sides, then I get second partial f with respect to x and y to be partial p with respect to y. Now here, if I differentiate partially both sides with respect to x, I get partial q with respect to x. But they both need to be the same. Thus, partial p with respect to y equals partial q with respect to x. And that is a big deal. What? I'll tell you why that is a big deal. That is a big deal because what is our question? Our question is the given vector field F, which is equal to Pi plus Qj, is that conservative? And what this has done is, it has given you a way of testing for it. If it turns out that you differentiate this P partially with respect to y, and that turns out to be equal to partial Q with respect to x, then you can be confident that your vector field F is actually conservative. That's the key. So we will keep applying that test. And in fact, how do you test whether a first order differential equation is exact? Let me take some medicine or something to get rid of this frog in my mouth here. Okay, I'm back. Sorry about that. Let me minimize that. Cool. Where were we? So, theorem. A vector field F equals Pi plus Qj is conservative if and only if partial P with respect to y equals partial Q with respect to x. So we can use this as a test. Yeah, I was mentioning in exact equations, you will look at partial, is this differential equation exact? Which one? Some m of xy dx plus n of xy dy equals 0. Well, is it exact? Well, if you take partial m with respect to y, and that turns out to be partial n with respect to x, then the equation is exact. This is very similar. Okay. Now, an important consequence of recognizing that f is conservative is with regards to integration. This is what I was talking about. Now understand that this is true only if f is conservative. You cannot apply, if f is not conservative, you cannot find f equals some del f. There won't be a function lowercase f such that f equals del f if f is not conservative. Okay, that means you cannot apply this process. But only if it is, then we got good news. This integral can be evaluated as just f of r of b minus f of r of a. I'll show you quite a few problems based on that. Okay, first let's start with this. Determine whether or not f is a conservative vector field. If it is, find a function lowercase f such that del f is equal to uppercase f. And the function happens to be this guy. Okay. Quickly, can you see what the strategy is going to be? From the previous one, the strategy should be very clear. A vector field f equals Pi plus Qj is conservative if and only if partial P with respect to y is equal to partial Q with respect to x. Do we have a scenario like that? Do we have some f of xy is equal to some P of xy I plus Q of xy j? Yep. So what do? We have P, we will identify what P and Q are, and then we'll verify whether partial P with respect to y equals partial Q with respect to x. As simple as that. Now, do I need to insult your intelligence by asking, hey, how do you differentiate this partially with respect to y? With respect to y, okay, that's clearly product rule. Right? There is a y function of y here and a function of y there. So they are multiplying. So first function y squared times the derivative of the second function is e to the xy times the derivative of xy is x. Plus second function e to the xy times the derivative of the first function 2y. And then just multiply this out. Xy is xy squared e to the xy. Now q with respect to x. First function 1 plus xy times the derivative e to the xy times the derivative of xy is just y plus e to the xy times 0 plus y. Cool. And so that's xy square e to the xy, and notice there is a 1 times y e to the xy. So there's a y e to the xy there, and there's another y e to the xy here. So that made it 2y e to the xy. Hey, lo and behold, these two guys are the same. So we have verified that in fact partial p with respect to y equals partial q with respect to x. And so this is in fact a conservative vector field. Cool? Okay. Now they're saying find a function f such that del f is equal to f. Again, if you have already taken differential equations, you will notice that we are going to do something pretty similar to what we did with exact equations. Okay. Here, to find this lowercase f, would you agree that partial f with respect to x is nothing but p, and partial f with respect to y is equal to q? We saw that in the previous section. Trust me on that. So, partial f with respect to x turns out to be this. Can we use that to figure out lowercase f? I don't know, man. What do you mean you don't know? You do. Let me give a simpler example. If I say dy dx is equal to x, dy dx is equal to x, can you figure out why? Yeah, you say dy is equal to x dx and you integrate. So y equals x squared over 2 plus c. So that means in order to find f, guess what? We could integrate this with respect to x. Integrate? But this is a partial derivative. Okay, do a partial integration. What the hell is partial integration? Well, partial integration means, just like partial derivative, if you are partially integrating with respect to x, hold y as a constant. Think of y as just a constant. Cool. So that's what we're going to do. For f of xy, we'll integrate p with respect to x. That means here p happens to be y squared into the xy. We are integrating that with respect to x. Y squared is a constant, so I can yank it outside of the integral. E to the xy integrated with respect to x. What is that? Well, e to the ax, integral of e to the ax dx is e to the ax over a. Now y is playing the role of a. So the integral should be e to the xy over y with a y square yanked out. So that's what I'm saying here. Y square e to the xy over y. Okay. Plus the integration constant. Hey, how come you're not saying plus c, man? What's up with the g of y? Well, here is the idea. When we are doing the regular integration, not a partial integration, the constant that we add has to be just a constant. But here, guess what? This could be a function of y. How does that work? Well, do you remember this concept? If you integrate something and you get something, you can always check that. How? By taking the derivative of this, you must get the integrand. Right? If I say integral of this is equal to this, then the derivative of this right-hand side must equal the integrand. Well, clearly when you differentiate this with partially with respect to x, you'll get y squared into the xy. That's a guarantee. However, what is more interesting is, what do you get if you differentiate partially g of y with respect to x? Oh, that's going to be 0. That's not going to affect the integrand. So basically what I'm saying is g of y is a more generalized constant. It is sort of akin to something similar to, okay, when you integrate, you get a constant plus c. Why don't you say plus 2 or plus 3? Well, you could, but that constant need not be plus 2. It could be plus 7. It could be plus pi. So we leave it as an arbitrary constant. So in this case, in a similar way, we leave that constant as an arbitrary function of y. Okay, that's something that you need to be careful about. Okay, now what? Are we done? Find f. Hey, we found f. Not quite. Because what in the world is this g of y? There is actually a way to finding g of y. And what is that way? Well, the f that we found here has to satisfy two conditions. One condition is that partial f with respect to x must equal y square a to the xy. And by integrating when we found f, sure enough, it does satisfy the first part. But what's up with the second part? Partial f with respect to y must also equal q. That is what we are going to exploit to find what in the world g of y is. So to do that, let me, by the way, I simplified it, y to the xy. Now what we do is, we will set partial f with respect to y equals q. It's important to read this statement, set, which means we are going to take the partial f with respect to y and make it equal to q, because it has to be equal. Those two things have to be equal. So we are forcibly setting them equal. For what reason, you will see in just a second. So first, do as I'm suggesting. Take the partial f with respect to y. Take the partial of this guy with respect to y. Well, partial of this with respect to y. Again, product rule, right? You can do that, I'm sure. And what is important is, what's the derivative of this guy with respect to y? This is just a g of y. It's purely a function of y. So when you differentiate partially with respect to y, because it's purely a function of y, you don't even have to do partial derivative with respect to y. It is exactly the same as the regular derivative y. That's the key to recognize. Cool? So as a result, what's going to happen is, I apply the product rule, plus g prime of y is what we get. So please pay attention. This stuff, these three terms, came by me differentiating this partial f with this f of xy with respect to y, the left hand side. Now I'm saying we must set that equal to q. So on the right hand side, I'm saying this is equal to so much for my medicine, man. That frog didn't go away. 1 plus xy e to the xy. So I set this equal to the q. Right? Why? What does it do? Well, notice there's a e to, these two quantities are equal. There's a e to the xy on this side, and there's a e to the xy on that side. And they cancel, or you can subtract e to the xy from both sides, and disappears. There's a xy e to the xy here, and there's a xy e to the xy. They cancel. And that means g prime of y must be 0. Aha! By doing this, what did we find? We found an expression for g prime of y. Can we figure out what g of y is when you know that? Yeah, integrate that. So when we integrate g prime of y with respect to y, we get some constant k. What? Integral of 0, is that not equal to 0, man? No, it could be any constant. Why is that? Because the derivative of any constant is 0. Right? So g of y is equal to k, some constant. Okay. What was our objective? What in the world were we supposed to find? Find a function f. Cool. Up here we had f of xy is y e to the xy plus g of y. We almost found f, except that we didn't know what g of y is. Now, based on this, we found that g of y must be some constant k. So, we'll say, ladies and gentlemen, f of xy is equal to y e to the xy and plus k. That's the final answer. But what is k, man? You cannot find k at this stage. If they gave you some value, for example, if they said lowercase f of xy is equal to lowercase f at 0, 0 equals 5 or something like that, then you can plug and figure out what k is. You have to be given a value of lowercase f at some xy. If that is done, then you know k. Otherwise, it's just a constant. K is a constant. Cool. All right. I hope this made sense. Let's do a few more. Find a function f such that del f equals f. And B is use part A to evaluate this integral. Cool. So they've given us this. I think they are saying, let me see, and they have given a C also. Well, they are saying, I think when they said find a function f such that del f equals f, they must have meant that you don't need to check that this is conservative, this f is conservative. It would automatically be true. But I have a feeling I may have gone ahead and tested it. We will verify whether, yep, I'm a good boy. So let's check, is their claim true? If we can find del f equals f only if f is conservative. They didn't say it's conservative, so let's check whether it is. So it's a simple process, partial p with respect to y. Let's check that, and partial q with respect to x. Well, they both turned out to be the same. So yes, we can find this is conservative, so we can find a lowercase f. What process do we apply? The same process as we did before. That is, partial of f with respect to x has to be equal to p, and partial f with respect to y has to be q. So we can integrate the p with respect to x, right? Now you might ask, wait. Why do you figure out f, lowercase f, by integrating p with respect to x? Couldn't you figure out f by integrating q with respect to y? If you actually thought that, you should pat yourself on the back. You are mighty clever. And you are in fact right. So the thing is, to find lowercase f in the first part, we have two options. Either we can integrate p with respect to x or q with respect to y. So let's take a look at this. Just a quick look at it. Is it okay to integrate this with respect to x? 1 plus xy e to the xy. That's e to the xy. Integrating e to the xy with respect to x is simple. But then xy e to the xy. That's integration by parts. Doable, but a little bit of a pain. Okay, let's look at this if this is any easier. X square. Oh, that's just a constant because we are integrating with respect to y. E to the xy. Oh, piece of cake. Integral of e to the xy with respect to y is e to the xy over x. So we are better off integrating q with respect to y in this case. And that's precisely what I'm going to do. Maybe I should have said equals integral q dy and then done this. Okay. And that turns out to be x squared e to the xy over g plus, what's the constant? Quote unquote constant, some g of x, right? Please be sure to call that as some kind of a function g of x. Now, and that reduces to x e to the xy plus g of x. Now, this time, what do we need to do? You remember in the previous problem, after we integrated p with respect to x, then we set partial f with respect to y equal to q. But here we do the opposite. That is, because we figured out f by integrating q, now in the next step, let's involve p. How do we involve p? By setting partial f with respect to x equal to p. So let's do that. Well, let's take the derivative of this partially with respect to x. And that's what we get. And the derivative of g of x is g prime of x. And that is equal to, let's let that equal to p. P happens to be, I think here I distributed it and said e to the xy plus xy e to the xy. And like before, e to the xy, e to the xy cancel, xy e to the xy, xy e to the xy cancel, and we end up with g prime of x to be 0, which means g of x is equal to some constant k. And so f is x e to the xy plus this constant k. Cool? All right, so that's the part A. Find a function such that del f equals f. Now they're saying use part A to evaluate this integral, this line integral, where c is given by this one. So let's do that in the next slide. But recall, the whole advantage of doing this, figuring out that this is a conservative vector field, and because it's a conservative vector field, I can find a corresponding lowercase f and all that nonsense, is because this integral simply becomes f of r of b minus f of r of a. What do I mean by that? Well, r of t is given to be cosine ti plus 2 sine tj with 0 to pi halves, right? So that means, that means what? Does that mean I can figure out r of b? R of t is this, a is 0, b is pi half. Yeah, r of b is r of pi halves, and r of a is r of 0, and that is, I just plug t equal to 0. Cosine 0 I plus 2 sine 0 j, and cosine 0 is 1, so 1 I, sine 0 is 0, so this whole thing goes to 0, and we just get r of a is equal to I. R of b, on the other hand, or the starting point of the, what am I saying? Or the starting point of the curve is x equals 1 and y equals 0. Where am I getting that from? And why do I need that? I'll tell you in just a second. R of b, on the other hand, is b happens to be pi half. So r of pi half, which is cosine of pi half, and that turns out to be 2j. Because sine pi half is 1, cosine pi half is 0, we end up with 2j. Or the ending point of the curve, what? The starting point happens to be just I. Is that the same as 1i plus 0j? Is that the same as x equals 1, y equals 0? Yes. Now, what do I mean by vector 2j? Is that the same as 0i plus 2j? So does that mean the ending point is x equals 0, y equals 2? Yeah. Okay, but why do you need that, man? Well, we need to find f of r of b, right? What is that lowercase f? We did that in the previous slide. Hey, that lowercase f is f of xy equals x e to the xy plus k. So that f is actually being given in terms of x and y. You agree? So what we need to do here is we need to, in order to find f of r of b, we need to say what r of b is in terms of x and y values. And that's exactly what we are doing. R of b corresponds to x equals 0, y equals 2. So f of xy, since f of xy is this, f of r of b is f of 0, 2. And which means plug 0 for x and 2 for y. 0 times e to the 0, e to the 0 is 1, 0 times 1 is 0, that's why I have 0, plus k. So f of r of b is just k. Cool. F of r of a, on the other hand, is we need to plug x equals 1 and y equal to 0, right? That's what this says. So f of 1 comma 0 is 1 e to the 0, which is 1 plus k. So we have 1 plus k. And now are we ready to figure out the desired integral? Yeah. So f of r of b minus f of r of a. So that is f of r of b is k minus 1 plus k. That's negative 1. Cool? Isn't that neat? I know, man, I don't know. It's way too much stuff. It just went over my head. That's why pause the video, repeat, maybe rewind and watch it again, and pull out a pen and a paper and solve this problem by yourself. But you will appreciate that there's a problem like this. F of xy is this, c is this, and you are expected to find this integral, this line integral. Whoa, that is pretty involved. But our method actually made it look as if it's not so bad. Somewhat, it's tedious, but welcome to college. That's how things are going to be from now on. But as long as the process is clear to you, you are in a good shape. Cool? All right. Whoa, that's it, man. Yep. If you learned that much, if you learned this much, you have learned a lot. All right, folks? Cool. Let's stop there then.